Take a look at these two containers, a steaming cup of hot water and a large bucket at room temperature. You might assume the hot cup holds the most energy, but the reality is the opposite. The bucket actually holds more thermal energy. Thermal energy represents the total sum of all that molecular movement. The bucket wins the energy contest because it has vastly more molecules. Even though they are moving slower, their sheer volume means the total energy pool is significantly larger. When we shift from measuring intensity to measuring total quantity, our entire perspective on the physical world changes. To see this principle in action, consider the interaction between an ice cube and a steaming mug of hot chocolate. What you are witnessing is heat at work. Physics defines heat as thermal energy actively transferring from a hotter object to a colder object. This movement continues until the system reaches equilibrium, where everything shares the same temperature. This energy transit originates from two categories. Natural sources include geothermal vents and the massive nuclear furnace of our sun, while artificial sources range from household ovens to hairdryers. Ultimately, heat functions as a continuous, active transit system, rather than a stationary state. As objects absorb this moving energy, their molecules speed up and demand more room to bounce around. They occupy more physical space, a rule known as thermal expansion. Objects typically expand when heated and contract when cooled. Curious, though, this rule creates a specific puzzle. If materials shrink as they lose heat, why do cold water pipes burst from the inside during a hard freeze? Observe this chart. As water cools, volume decreases normally until 4 degrees Celsius, then reverses. From 4 down to 0, volume increases. This means water achieves its maximum density at exactly 4 degrees Celsius, the critical point illustrated by the compact molecular structure here. This refusal to follow the standard rules of expansion is the specific reason winter pipes burst under pressure and why ice remains buoyant on the surface of a lake. We see another thermal mystery on summer playgrounds. A metal slide becomes hot enough to burn skin, yet the wood chips right beneath it stay cool in the exact same sunlight. This occurs because of specific heat capacity. It measures a material's internal resistance to changing its temperature when heat is applied. We test this by heating 3 different metal spheres to 400 degrees and dropping them onto solid wax. The metal with the highest specific heat capacity sinks deepest. Because it required the most energy to heat, it releases a sustained reservoir of energy, remaining hot. Materials with high specific heat capacity function as thermal batteries, absorbing, storing, and slowly releasing vast amounts of energy. We can observe these batteries on a global scale by looking at the thermal dynamics of a beach. Liquid water possesses a massive specific heat capacity compared to dry sand. The ocean requires far more solar energy to warm up, meaning it changes temperature at a much slower rate than the land. This imbalance creates a sea breeze. During the day, the fast heating sand warms the air directly above it. As that hot air rises, cool air from the ocean sweeps in to replace it. At night, the cycle reverses, as the sand loses heat rapidly while the ocean retains its thermal store. This same lack of storage in sand is why deserts fluctuate from boiling afternoons to freezing nights. The differing thermal properties of dirt and water dictate the airflow, weather patterns, and winds of our entire planet. This entire system follows the law of calorimetry. It dictates that in a closed system, the heat energy lost by a hot object will always perfectly equal the heat energy gained by a cold object. This single law connects the dynamics of a hot cup of water to bursting winter pipes, melting blocks of wax, and massive global weather. Heat serves as the invisible, mathematical flow of energy, constantly working to bring a chaotic universe into perfect equilibrium.